Python control flow, branching and looping structures. Python has what is called a top-down flow of control. The flow of control, sometimes referred to as control flow, is the order in which variables, statements, and expressions in the code are executed. To help demonstrate this, I'm going to turn on the line numbering in Jupyter Notebook by pressing Shift-L. You can also access the option in the View menu. Now I'll write x-coordinate equals -123, and then print x-coordinate. When I run the cell, Python reads the first line of code and assigns the value -123 to the variable x-coordinate. Then it reads the next line of code and prints x-coordinate to the screen. Now I'm going to go to the next cell and I'm going to type in x-coordinate. When I run the cell, you see two things happen. I have an in value and an out value, both of which have the number 2. You'll only ever see the out label in Jupyter Notebook when your script is returning a value. So printing to the screen is something different than returning a value. It's a subtle difference, but important depending on the way you use your variable. The number 2 indicates the order of execution by cell. So the cell with the number 1 next to it was executed first, and the cell with the number 2 next to it was executed second. You may also notice that Jupyter Notebook keeps track of the value of the x-coordinate, even though I typed it in a different cell. Additionally, the line numbers within each cell always restart with the number 1. So, confused yet? Just remember that in and out numbers refer to the execution order of the cells. The line numbers refer to the order of execution of the code within the cell. It should make more sense the more you work with code in Jupyter Notebook. Okay, so far so good. It looks like Jupyter Notebook is following the top-down control flow. I defined the x-coordinate variable at the top, so when I refer to the variable further down on the notebook, it understands what it means. Next, I'll demonstrate what happens if I break the flow within a cell. I'll add a second variable, but this time, I'll write the print statement first. Print y-coordinate, then y-coordinate equals 41. I'll press Shift-Enter to run the cell. When I do, I get a name error. Name y-coordinate is not defined. So what happened here? If you look closely at the error message, you'll see an arrow pointing to the line where the error occurred. In this case, it's line 1 where I placed the print statement. When Python reads line 1, it does not know about the y-coordinate variable in line 2. Because it does not know what to do with it, it stops running the code at line 1 and returns an error. It never gets to line 2. I'll fix it and rerun the cell. Now there's no error, because by the time Python gets to the print statement, it knows what the variable y-coordinate means. This is what I mean by a top-down flow of control. For the most part, the top-down flow control doesn't pose too many challenges. People are used to reading from the top, so the fact that Python does it too feels natural. However, working in Jupyter Notebook adds some additional complexity. In Jupyter Notebook, this flow control is only consistently enforced within a specific cell, and not necessarily between cells. I'll show you what I mean. I'm going to add a new cell at the top and print the y-coordinate. When I run the cell, it works fine. So why didn't I get an error? The print statement is at the top, and I defined the variable at the bottom. This seems like breaking the rules of top-down control flow. What is happening here is that when it comes to cells interacting with each other, Jupyter Notebook only cares about the order of execution. Notice the number next to the cell at the top. The number at the top comes after the number at the bottom. The ordering of the cells on the page doesn't matter. Only the order of execution matters. So what happens if I delete the cell that defined the y-coordinate? To do that, I'll select the cell and press DD on my keyboard. Pressing DD on the keyboard deletes the selected cell. When I rerun the cell at the top, it still works. Okay, so you might be thinking that things are getting kind of screwy. If I deleted the cell, why is it able to use the variable? Even though I deleted the cell where I defined the y-coordinate, the variable and its value are still stored in the computer memory. To explain, let's rewind back to when I created the notebook. When I first created the notebook, it started what is called an IPython kernel. An IPython kernel is a computational engine that executes the Python code contained within the notebook document. You can think of an IPython kernel like a car engine. Once you start it up, it keeps track of all of the inputs and variables that were ever executed while it's running. As long as the engine is running, it remembers. However, when you turn off the engine, it forgets everything. When you restart the engine, it starts from a blank slate, as if none of the cells were ever executed. Right now, I'm at a point where I just started my notebook, so it's like I just started my car engine for the first time, and it's happily running under the hood. I'll call the directory function and run the cell. The directory function returns a list of variables and functions currently available in this instance of the IPython kernel. This is what you get automatically when you start the engine. For example, it includes all of the normal built-in functions that come with Python. Right now, however, I haven't defined any variables, so there are no variables in the list. Okay, so I'll define a couple of variables and run the directory function again. First name equals Nicholas. Last name equals Malloy. Now I'm going to run the cell. Even though I haven't printed anything or returned any values, I've created some variables using an assignment statement. Because I ran the cell, these values are stored in the IPython kernel. Now I'll run the directory function again. This time I can see that my two variables were appended to the list. The kernel stores them in computer memory. I'll delete the cell by selecting it and pressing the D key twice. Then I'll run the directory function again. As you can see, the variables are still on the list. The only way you can wipe them from computer memory is to use the delete function or restart the engine. Okay, so I'll delete the variable first name. And then I'll run the directory function again. Now you can see that the variable first name is not on the list. If I try to print it, I get a name error. According to the kernel, it does not exist. Now I'll rerun the cell where I defined the two variables and check the list. Both variables are back. Next, I'll try restarting the engine. You can do this by clicking on the Restart button on the toolbar. Now I'll run the directory function again, and both variables are gone from the list. If I try to use them, I get an error. So you can see that maintaining control flow in Jupyter Notebook has the potential to get really messy. You can avoid complications using some best practices. Let's return to where we left off earlier. I'll restart the kernel so everything gets wiped from computer memory. So the best practices are to always organize your notebook so that the cells are arranged in the order that you want them to be executed. It should flow logically from top to bottom. That means declaring variables before you use them. Another best practice is to only use multiple cells when necessary. If you're writing a complex program, each cell should contain a block of code that has a standalone purpose. Even though I'm not writing a complex program, I can still group all of my code into one cell. I'll start by declaring my variables in the cell at the top. Then I'll delete all other unnecessary cells. So if my goal was to define two variables and then print them out, I can do all of that in just one cell. Branching control flow. Sometimes, a top-down control flow isn't enough to accomplish your programming objectives. Branching control flow offers one way to add some flexibility into your program. So what do I mean by branching? In computer programming, branching allows the flow of execution to jump over parts of your code depending on the conditions you define. It works just like a decision tree. When Python encounters a branching statement, it checks for a condition. If the condition is met, it executes one part of the program while skipping over other parts. If the condition is not met, it executes a different part of the program. There can be any number of conditions. Each time, Python jumps to a specific section of code and skips over another. Python uses the keyword if to begin a branching statement. The syntax looks like this: if condition, colon, do something. Elif condition, colon, do something else. Else, colon, do something else. Let me show you how it works. I'll write a snippet of code that works like a magic 8-ball. To begin, I'm going to import a module called random. I'll talk more about modules later. For now, all you need to know is that a module is a separate file that has some pre-written code that you can use when you need it. I have to import the random module because it has some functions that are not included automatically. To import the random module, I'm going to type import random. I need to make sure that this import statement gets executed first before I try to use any of the functions in the random module. Following best practices, import statements should be placed at the top of your notebook so that the standard top-down control flow brings in the modules you need. In this instance, I don't need it for my earlier code, so I'm going to place it in a cell at the beginning of this section in my notebook. I'll run the cell so that the kernel now has access to random. In the next cell, I'll create a variable that instructs the user to ask a question. I'll add an escape sequence at the end, \n, so that the user's response appears on the next line. Next, I'll create a variable that holds a random number between 0 and 2 using a function called randint. The syntax for calling functions from a module is module name followed by a dot, followed by the function name. So I'll begin with creating a variable the usual way. Then I'll type in the name of the module I want to use. In this case, that's the random module. I'll type a dot, and then notice if I hit the tab key, I get a list of all of the functions available in random. I'll scroll down and choose randint. The randint function accepts two arguments, the starting number and the ending number. When you run it, it will return a number between 0 and 2 with the integer data type. Because it's part of an assignment statement, the random integer gets stored in the variable answer. Now I'm going to start the branching control flow using an if statement. If the variable answer is equal to 0. Now I have to end my if statement with a colon. If you forget the colon, it won't work. When I press enter, notice that the next line is automatically indented. Python uses indentation to define a block of code. All lines next to each other with the same indentation level belong to the same block. You can use indentation to nest code blocks within other code blocks. In this instance, my next line of code is considered nested within my if statement. I want to give a negative response if randint returns 0, so I'll create the variable message equals probably not. So to recap, I'll start by defining two variables, one to request user input, the other to store a random number between 0 and 2. By the time Python gets to the if statement, the answer variable already has an integer ready to go. The if statement checks to see if the integer is 0. If it is, Python enters the nested code block and creates the message variable with a negative response. Okay, so what if the integer is not 0? If that's the case, Python will not enter the nested block of code. Instead, it will look for the next line that has the same indentation level. That means that I have to make sure that my next line is not indented. It has to line up with the if statement. I'll type elif answer is equal to 1, colon. The elif keyword stands for else if, and it works just like the if statement. In this instance, if the answer has a value of 1, then it will send an affirmative response. Message equals, it sure looks like it. You can have any number of elif statements to check for multiple conditions. If none of the conditions match, then you can use the else statement. The difference is that an else statement does not have a condition. It just executes if none of the previous conditions were met. Just make sure that the indentation level lines up with the initial if statement. This time I'll provide an ambiguous reply. Else colon, message equals, I have no idea. Once Python encounters the else statement, then it stops looking for conditions and executes the nested code block. Then it jumps over to the next line of code. I'll have Python print the message to the screen, print message. So let's test it out. I'll run the cell and provide a question. Is it going to rain today? Looks like it's working. This was a very simple example. However, branching structures can be as complex as you need them and provide a lot of flexibility for your programming needs. Looping structures. There may be times when you want to repeatedly run a block of code until certain conditions are met. Instead of retyping a block of code over and over, you can incorporate a looping structure. There are two looping structures that are commonly used, the for loop and the while loop. For loops repeat an action for each item in a sequence. If you'll recall, sequences include data types like strings, lists, and tuples. Let me show you how it works. I'll start by creating a list of countries that belong to the European Union. So I'll type EU countries equals, then I'll start a list of all the countries in the EU. This list is long, and trying to type them out on one line will make the code hard to read. According to PEP 8, you should limit all lines to a maximum of 79 characters. To make my code easier to read, I'm going to hit enter after every third country. I believe that should keep the total line length under 79 characters. I'll start by printing out this list just to make sure it works. I forgot my closing parentheses. Okay, looks good. As you can see, when I print the list directly, it gets printed in list format. So what if I just wanted the name of each country printed out by themselves on each line? Or maybe I wanted to do something with the names in the list, like include them in a message to print to the screen. One way to do that is to write a series of print statements and use the index number to differentiate between items on the list. I'll show you what I mean. I'll start with a regular print statement and then pass in the EU country with an index of 0. Then I'll test it out to make sure it works. Now, to get all of the countries in the list, I would have to write a print statement for each country. Something like this. I'll just change the index number for each instance of the print statement. You get the idea. So you can see that this would become tedious right away. Imagine if I had a list with hundreds of items in it. Doing it this way would be problematic. An easier way to do this is to use a for loop. The syntax goes something like this. For variable in sequence, colon, then on the next line, indented, do something. The keyword for triggers the start of the loop. The variable will temporarily hold the value of each item in the list. It's created automatically, and you can use any name you want, as long as they follow best practices. Next is the in keyword, which checks to see if a value is present in the sequence that comes next. Then you indicate the name of the sequence variable and close the loop with a colon. So for this loop, I'll type for item in EU countries, colon. When I press enter, the next line automatically indents. So whatever actions I put here are going to be nested within the for loop. I'll have Python iterate over each item in the list and print the name of the country to the screen. I'll press Shift-Enter to run the cell, and I get the results I want. As you can see, this is a lot easier than typing in a bunch of print statements. If I wanted to, I could make it more complex by nesting in an if statement. For example, if the country begins with the letter P, I want the program to print out, I want to go to, and then the name of the country. I'll show you what I mean. First, I'll copy my for loop into the next cell, and then nest in an if statement. If item index 0 is equal to capital P, colon, the 0 index will grab the first letter of the country name. Next, I'll write out my print statement. It'll have to be nested within the if statement. Print, I want to go to plus item. So you can see for loops can be used in many ways and save you a lot of time. While loops. A while loop is a condition-controlled loop. It performs an action repeatedly until certain conditions are met. The basic syntax goes like this. While condition, colon, do something. The while keyword begins the loop. Next, you define a Boolean condition that is equal to true or false, followed by a colon. The next line will be indented so that whatever action you define is nested within the while loop. Once the condition is no longer met, Python pops out of the loop. Let me show you how it works using a simple example that increments a value. First, I'll create a variable and set the value to 0. X equals 0. Then I'll start my while loop. While x is less than or equal to 10, colon, If the condition is true, I'll have the program print the value of x to the screen, print x. Then I'll increment x so that each time the program loops, 1 gets added to the value of x. X equals x plus 1. Last, I'm going to include a print statement outside of the loop so that I know when the program is done looping. This type of print statement is useful for checking the condition of the loop. It's not something you would normally include in a finished program. Let's test it out. I'll press Shift-Enter to run the cell. Okay, so I'll just break down what happened. On line 1, we have an assignment statement where x is equal to 0. The while loop starts on line 2 where it checks the value of x and compares it to 10. So if x is less than or equal to 10, then Python will jump into the loop on line 3. If it's not less than equal to 10, Python won't jump into the loop. Right now, x is equal to 0, and since 0 is less than 10, Python jumps into the loop on line 3 and prints x to the screen. On line 4, there's another assignment statement that sets the value of x to x plus 1. So right now, x is 0, and 0 plus 1 is 1. So x is now equal to 1. The program jumps back to line 2 and checks the value of x again and compares it to 10. Since 1 is less than 10, the condition is true, and Python jumps back into the loop on line 3. It prints x to the screen, which right now has a value of 1. And then on the next line, it increments x again. It does this repeatedly until x is equal to 10. It prints x and increments x one more time so that now x is equal to 11. The while statement checks the value of x and compares it to 10. And since 11 is greater than 10, the condition x is less than or equal to 10 is false. Since it's false, Python doesn't jump back into the loop and executes the next line that has the same indentation level. In this instance, that's the print statement that says the loop is done. One of the dangers of using while loops is that there might be times when the condition is never true or never false. Let me show you what I mean. First, I'll set the value of x to 11 and then run the cell. Because x is never less than or equal to 10, the condition is false, and Python skips the loop altogether. This is fine as long as it's the way you intended for the program to work. On the other hand, what happens if the condition is always true? To demonstrate this, I'm going to change the condition from x is less than or equal to 10 to x is not equal to 10. Because line 1 sets the value of x to 11, and the loop increments x up by 1 each time, x is always going to be not equal to 10. This is what's called an infinite loop. I'll press Shift-Enter to run the cell and show you what I mean. The program now has an infinite loop and will run forever until something outside of the program forces it to stop. I'll use the stop button on the toolbar to break the loop. When writing while loops, you always have to consider how you're going to avoid this from happening. In this instance, the problem is with my condition. If x is ever greater than 10, the result will be an infinite loop. If I absolutely had to use the not equal operator, I can use other strategies to handle this situation. For example, I can use a nested if statement that checks for a condition that would result in an infinite loop. If x is greater than 10, break. The break keyword breaks out of the current loop and goes to the next line with the same indentation level. I'll run the cell and check to see if this works. As you can see, while loops require careful consideration and planning. However, while loops are very useful especially when you're not sure when certain conditions will be met, and you need the program to continue running until they are. Don't forget to subscribe to this channel for more videos and tutorials related to geospatial science.